I'll talk a little bit about wavelet phase retrieval. And specifically, I kind of gave a similar talk like this before at Vanderbilt a while ago. But today I have significantly more time, so I think I can show you the proof of the main result. And I hope you will enjoy that. And specifically, I hope that Radu might enjoy it, because we're going to see the complement property in use, not only once, and also not twice, but 3 times. So, right. Great. Okay, so before I go into this, let me first say that everything that I'm going to present is joint work with Rima Alakari and Jessica Bartolucci. And I think then we can start. So, okay, there we go. Okay, so the first thing I want to do is I want to introduce the wavelet transform. And, well, first of all, let me say that an L2 function is a wavelet if its Fourier transform at 0 is 0. In other words, if its mean is 0, so if you just integrate over phi, that is 0, then we say that the function is a wavelet. And sort of there is a little bit of intuition to this. If you look at this picture, if the mean of a function is 0, suppose that the function is non-zero in real value, then it needs to go below 0 at some point, and it needs to go above 0 at some point, so it kind of looks like a wave. That's why we call it a wavelet. Now, the wavelet that we have here is a special wavelet. It's one that we will see a lot today. It's the so-called Poisson wavelet. We're going to work with that quite a bit. But that's for later. Okay, so now the wavelet transform of a signal f, also in L2, is given by this integral transform, which is kind of all I want to say about it, or all I want to say about this point. But then, if you were to introduce the translation operator T and dilation operator A, then you could also write the wavelet transform as the inner product of f with translated and dilated wavelet. So I think it's just like a little bit of basics. I think the only thing that people that already know the wavelet transform, the only thing that is slightly interesting is that for the convention we use the dilation that is L2 isometric instead of L1 isometric. But that's about it. Okay. So this is the wavelet transform. Now, for practical purposes, what we do quite often is that we do not take the entire wavelet transform, but we will only take samples of the wavelet transform. And we typically do that on things called hyperbolic lattices, which, well, yeah, you can see it here on the slide. We will use this set lambda, beta, alpha quite a lot, so it's good to get used to this notation, lambda, beta, alpha for the hyperbolic lattice. Let me also quickly just show you what that looks like, just so you get a feeling. So here in this picture, the beta almost doesn't matter. This is a beta that will play a role later on, but okay, it's just some kind of beta, but you see alpha is equal to 2, and this sort of has some importance, because now you can think of like what happens at the individual scale. So for instance, if we start at this scale up here, so this would correspond to m being 3. So alpha, which is 2, so 2 to the power of 3 is 8. This is the 3rd scale, let's say. You see there is a certain distance between these points. So they're like equidistant points at 8. And then if you go down one scale, so to 4, then you see there are twice as many points in any interval. So every time you go down, points get twice as close to each other. And that's sort of this hyperbolic lattice that we're sampling, just as a picture. Right. Okay. So now that we have the hyperbolic lattice, what we can do is we can take a collection of the wavelets. Specifically, we take translation, dilation of the wavelet at the hyperbolic lattice. Okay? And we will call this entire collection of functions a wavelet frame. And now here I'll say it's a wavelet frame for some subset of L2 if the frame condition is satisfied. So this condition is what we usually require of a frame, and I think I'll leave it at that because it's quite common in these sort of talks. Okay, so if we have a wavelet frame, so if this calligraphic W is a wavelet frame, then what we can do is we can stably recover our signal f from the wavelet coefficients W, phi, f, EA on the hyperbolic lattice. Okay, so that's like a short introduction to the wavelet transform. Now, what we are going to do today is something that is slightly harder than recovering f from the wavelet coefficients. What we're doing instead is we're trying to recover f from the magnitudes of the wavelet coefficients. And this problem is called wavelet phase retrieval, or more specifically, if you take hyperbolic lattice, we'll refer to it as sampled wavelet phase retrieval, which refers to the fact that we're not taking information everywhere, but just on the hyperbolic lattice. Right. Right. So there's an immediate problem if you look at any phase retrieval problem, in fact, which is that if you think of f and e to the I theta f, then both of these signals generate the same measurements because they will be absorbed by the absolute value once you use the linearity of the wavelet transform. Okay? So the typical thing that we do in phase retrieval is we introduce an equivalence relation on L2. F will be equivalent to G if and only if f is equal to e to the I theta g. So basically say we don't care about this ambiguity that is inherent to the problem. And there is some, at least in the very few things that I know about, very few application things that I know about, let's think of audio processing applications, for instance. This is perfectly fine because humans can't hear this ambiguity. Whether you play f or minus f with your computer, it's not something a human can tell apart. Okay, so that's that. Now, mathematically speaking, I want to introduce a phrase which is doing phase retrieval. So what I will use quite a lot during this talk is I will say that a frame does phase retrieval if the corresponding operator, calligraphic A here, and so what is A? So it will take an element of H, which is a subset of L2, modulo this equivalence relation into L2 by just associating the magnitude of the wavelet coefficient. So we will say that a frame does phase retrieval if this operator is injected. It's kind of what you would expect. It's not a very surprising notion, but yeah, just want to introduce that. Great. Okay, so there is actually one more slide of introduction, which is that what we're mostly going to do today is, well, technically phase retrieval, but we will also refer to it as sign retrieval because, strictly speaking, it's a bit of an easier problem than the full phase retrieval problem. So how come? If both the wavelet phi and the signal f are real values, then it's not very hard to see, just from the definition of the wavelet transform, that the wavelet transform is real valued everywhere. So if you take the magnitude of something real valued, you're of course not discarding phase information, you're sort of only discarding the sign. So in order to recover that phase information, you're only recovering sign information, and we will talk about sign retrieval. Now it also has an impact on this equivalence relation, because once you know that f and g are real valued, the only two options you really have are that either f is equal to g or f is equal to minus g. And this is sort of going to play quite an important role later on, but it's sort of a simple statement. Okay, so and then the mandatory definition of the phrase doing sign retrieval is just, in a real value case, if you do phase retrieval, we'll also say we'll do sign retrieval just in order to not sound self-important, let's say. So it's technically kind of okay to say that you're doing phase retrieval, but we're going to say we do sign retrieval. Okay, so that's the introduction to phase retrieval or sign retrieval. So now I want to show you a little bit of earlier research on wavelet phase retrieval. And what I want to start with is maybe not the earliest paper that I know of, but sort of the paper that kind of started it all, at least for me, which is a paper by Mala and Waldsburger from 2015. And what they do is they start by considering the Cauchy wavelet, which is a specific type of wavelet defined in terms of its Fourier transform. So, I mean, I guess you could write it down in terms of its regular, like not in terms of its Fourier transform, but it has a very nice, its Fourier transform is very nice, so it's nice to write it down like this. And one thing that is easy to see here is that there are no negative frequencies that come up inside. So there are only positive frequencies inside, and so therefore we will say that the Cauchy wavelet is an element of the Hardy space, which is just all L2 functions that have no negative frequencies. Great. Okay, so what do they prove? So what Malan and Waldsburger prove is that if you have any A0 bigger than 1 and any two scales j and k, and so you see, I assume that j is strictly smaller than k, but that doesn't matter. You could switch the role of the two. So basically, pick any j and k that are not the same. then every element of the Hardy space is uniquely determined up to this equivalence relation that I defined before by the magnitudes of the wavelet transform at r times a0 to the j, a0 to the k. Okay? So this is sort of, well, this is what they prove. Now, I highlight the r times the a0 to the j, a0 to the k in orange because there is something that is sort of undesirable from this, which is that that's not actually a hyperbolic lattice. In fact, it's not a discrete set at all. So we would like to go from this to a discrete set. And there is a very simple trick that you can do here. We're eventually going to do something else, but I just want to point out that you can do a simple trick, which is you can say, okay, let's look at band limited signals, and I'll denote them by PW omega. PW stands for Peggy Wiener. And well, once you do that, you can just use a sample theorem and can say, okay, actually this uniqueness extends in some sense to sets of this form, which now are discrete, and these sets also are contained in hyperbolic lattices. So you can kind of go around this way, but it's really, you're getting a corollary of something that's already there, and we're going to take a different approach. Okay, but I just wanted to point this out. And well, part of the reason why I'm pointing this out is because before what we did, what I'm going to show you right now, most of the results that I know of, or all of the results that I know of, somehow involve some kind of band limitedness somewhere. So the first result that I want to show you in this theorem by Hema, Inke, Dogeshi, Philip Post, and what they showed in 2017 is that if you take a wavelet that is real valued and band limited, then you can find some beta such that the dyadic wavelet frame does sign retrieval on the exponentially decaying functions. So you can see there is some kind of band limitedness in the wavelet, and then also, well, you would have to think about this for, there seems to be background noise, which I'm not sure where it's coming from because it's quite quiet in this room. I think it's the projector.
Is it?
Oh, it's better now.
Okay, that is if you don't speak.
Okay.
Okay. Oh, maybe actually there is somebody who has the microphone on.
If everyone would please mute.
Yes.
Right.
Something like that. Yeah, okay.
Right. Yeah, I think I'll continue. I think there's nothing I can do about it from my end, so I'll just continue. Right, so yeah, you have this result where if you assume that if the wavelet is band limited, then you get sign retrieval on the exponentially decaying function. Now I have to think about this for a little bit longer, but exponentially decaying function sort of sounds a little bit band limited to me as well. But I don't know. So in any case, band limitedness is in here once. At least once. Okay, so then there is another theorem which we proved not too long ago, which I'm not going to talk about today, except that I will highlight it, which says that for any parameters that you choose, if you have a wavelet that has finitely many vanishing moments, then your wavelet frame will do sign retrieval on the real valued band limited signals. Which, that's a result I really like, but again, you can see there is a band limitedness assumption here to make it work. Okay, so the obvious question, and that's something that we're going to discuss today, is how can we go beyond band limitedness? So how can we get rid of this? And then I have a side remark on this slide as well, which is just a definition of finitely many vanishing moments, because I think it's kind of non-standard. And yeah, but it's in brackets because I'm really not talking about this today. It's just for completeness. Right. Okay, so let's move on. Next, I want to show you a few, well, they're not really basic, but they're preliminaries for the proofs that I'm going to show later on. And well, I forgot how many slides these are, but there are not a whole lot of them, so it will be easy to see. The first thing is, I want to introduce the Poisson wavelet. And just like the Cauchy wavelet, the Poisson wavelet is actually defined in terms of its Fourier transform. And if you look at this you'll notice, or you might notice one thing, which is that the Fourier transform of the Poisson wavelet is very symmetric. And so in particular, you see that the Poisson wavelet is actually real valued. So that's something that will be important. Now the Poisson wavelet and the Cauchy wavelet, which we have seen earlier on, are actually really closely related. And that relation can be seen in terms of the Hilbert transform, which I'll also just quickly introduce in terms of its Fourier transform. And that's really, so the Hilbert transform is probably a much more complicated transform that you can say a lot of things about, but basically the next bullet point is everything that we're going to need from it. So I'm just going to leave it at that. The next bullet point being that 2 times the Cauchy wavelet is the Poisson plus I times the Hilbert transform of the Poisson. And this is not, like, does not even, I notice, look quite as magical as it truly is yet, because you have to realize that the Poisson is real and the Hilbert of the Poisson is real. So this is really the splitting of the Cauchy wavelet into its real and imaginary parts. So that's kind of useful, and that's something we're going to use. Specifically, what we have is that if we take the Poisson wavelet transform of a real valued signal, then we get 2 times the real like the real part of the Cauchy wavelet transform. And the same, or something similar, being true for the Hilbert, for the Hilbert transform of the Poisson wavelet. Okay, so we get this kind of splitting, and that's sort of going to play some tricks for us later on. And so, right, so this is one thing. Now the second thing, this is half of the preliminaries. The second part of the preliminaries is the weighted Bergman space that I have up here. So the weighted Bergman space is a space of entire functions. That's what this O of H stands for. So O stands for entire functions, and H stands for the upper half plane. So these are holomorphic functions on the upper half plane that satisfy some kind of integral condition that I'm not really going to talk about today, even though we're going through the proofs. I'm not going to calculate any integrals. So basically, think of holomorphic functions on the upper half plane with symmetrical condition. Now, why do we care about the Bergman space? Well, we care about the Bergman space because if you take any L2 function and you take its Cauchy wavelet transform, then that is essentially an element of the Bergman space B3. Now, there is this a to the minus 3 on 2 in the front, but that almost does not matter for any of the proofs. I mean, we'll put it there just to be correct, but it doesn't really play a big role. Okay, so this has 2 very nice upshots. The fact that if you take the Cauchy wavelet transform of a function f, that will essentially give you a holomorphic function, has 2 very nice upshots. The first one is that if you think of the Poisson wavelet transform, or if you think of the Hilbert of the Poisson, then since those are the real part of the Cauchy wavelet transform and the imaginary part of the Cauchy wavelet transform, that will give you a real analytic function. That can be quite useful. And the other reason for why it is useful is almost kind of hidden behind this bullet point, which I admit is not ideal. The other reason for why it is useful is actually that we really know a lot about the Bergman space. So there's a lot of established theory about the Bergman space, and specifically the one paper that we're going to refer to multiple times is a paper by Christian Seif from 1993, in which, among other things, this sampling result here is proven. But, so yeah, I think I'm not even going to talk too much about this sampling result because, this is sort of not the main point. The main point is that there is theory that we can use. This is one way in which we use the theory, but there is another result that's similar to this, which is a uniqueness result. So basically, I think interesting is that if you have this kind of condition on beta log alpha here, then you get a sampling result, and if you have beta log alpha is smaller or equal than this, then you get a uniqueness result. That's kind of what we're going to use. Right. So these are the reasons for why this is interesting. So now, this sampling result, for instance, just to talk a little bit more about this, you can just take this and translate it into like what it means for the Cauchy wavelet transform, essentially, or for the Poisson and the Hilbert transform of the Poisson. What it means is this: so you get another frame condition immediately. Like you just translate it. I'm like not going through the details of this, but it's quite basic. So what it tells you is you get this frame condition, provided that beta log alpha satisfies the right condition here. And so what we're going to say is that if you take the Poisson and the Hilbert of Poisson, you get a multi-wavelet frame instead of just a wavelet frame. Because now instead of using one wavelet, you will use two wavelets. Right, okay. So in particular, you could, if you wanted to, stably recover a real value function from the Poisson wavelet coefficients together with these Hilbert of the Poisson wavelet coefficients. Right, okay, so those are all the preliminaries. Then we can move on to the results that we have and that we're going to prove. Before I show you the first result, I quickly need to introduce a little bit of notation. So this A of R times R plus will be the real analytic functions on the upper half plane. And now the first result that we have is this. So suppose that you have some subset of the upper half plane that has positive measure, and suppose that you have a wavelet that's real valued and also such that the range of the wavelet transform is real analytic. So sorry, if you take the wavelet transform with respect to that wavelet of any function, that will give you a real analytic function, is what I'm trying to say here. Then every real valued function is uniquely determined up to the equivalence relation that we had before by the magnitude of the wavelet transform on omega. Okay, so there are two things which are highlighted in orange, which I just quickly want to say, you might have noticed already. So the first thing is, you see there's no band limitedness here. That's why I highlight the L2 in orange. Now at the same time, you see we don't actually have like a discrete set. We have to take a set of positive measure. And we've been trying around with this quite a while and we couldn't get it like to anything better than this. Okay. So we have a solution, but I first, before I want to show you the next theorem, I quickly want to show you the proof of this because it's half page and I think that's quite nice. So before I do that, the remark here is that of course this applies to the Poisson and the Hilbert of the Poisson. Okay, so now let me show you the proof. I think it's enjoyable. So suppose that you have two real valued L2 functions such that their magnitudes agree, if the magnitudes of their wavelet transforms agree on omega, then there is the first application, let's say, of the complement property, where you say, okay, so I'll define a set S. That set will be the set on which the wavelet transform of F and the wavelet transform of G agree. Okay. Then I will define two functions, H plus being F plus G and H minus being F minus G. And if I think of F minus G, because the wavelet transform is linear, and because on S, the wavelet transform of F agrees with the wavelet transform of G, I must have that the wavelet transform of H minus must be 0. Okay? So that's just straight from the definition of the set S. And now you're going to use the fact that everything is real valued, because if everything is real valued, there are only two options. Either the wavelet transform of F agrees with the wavelet transform of G, well, we've taken care of that part. Or the wavelet transform of F does not agree with the wavelet transform of G, but in that case it must be minus the wavelet transform of G. So we're taking care of that with H plus. In this case, the wavelet transform of H plus must be 0. It's kind of the main, right? That's sort of the trick, saying the complement property. And so what does this mean here? So because omega has positive measure, either the complement of S or S must have positive measure, but both of these functions are real analytic, and a non-zero real analytic function has a zero set that has zero measure. That's a lot of zeros in there, but essentially that immediately tells you that either H plus must be 0 or H minus must be 0. And that's it. So it's really simple, but unfortunately we did not know how to go beyond a non-discrete set here. But one thing that one can do, and that we eventually ended up doing, is one can take more than just the Poisson wavelet transform. So we will take 3 wavelets here. We'll take the Poisson, we'll take the Hilbert of the Poisson, and we take the Poisson plus the Hilbert of the Poisson. And if we have measurements from all of these 3 wavelets, then we can do symmetry rule for the real values of 2 sigmas. And now like fully discrete. There's a bit of an extra trick here. we allow ourselves to take more measurements. And maybe just to give some intuition before I go into the proof. So thinking of it, the Poisson will give us information about the real part of the Cauchy-Wavelet transform. So once we have these measurements, we can say, okay, the real part of the Cauchy-Wavelet transform agrees well with the other real part of the Cauchy-Wavelet transform up to a sign. So the Hilbert of the Poisson will give us the same for the imaginary part. Okay, then it already sounds like, oh, you're getting towards the Cauchy-Wavelet transform. Well, there is sort of the hidden piece, which is the sum of the two, which gives us the connection between the two. Because if you don't have P plus HP, it could be that the sign on the real part is the opposite of the sign of the imaginary part. So this one connects the information that we have here. So that's sort of the idea. Okay, so then let's go into the proof. So assume that you have two functions, f and g, such that the wavelet transforms with respect to the Poisson, with respect to the Hilbert of the Poisson, and with respect to P plus the Hilbert of the Poisson agree on the hyperbolic lattice. Then there is the reformulation of this in terms of vectors in R2, which we're going to use, which is just this. So you say, I introduce a vector WH, let's say, because I want to apply to f and g. So WH being the Poisson wavelet transform on top and the Hilbert of the Poisson on the bottom. Introduce this vector. And then if I have these vectors V1, V2, V3, they will just correspond to the measurements of P, HP, and P plus HP, which I think is kind of easy to see, right? If you take the inner product of V1 with WF, for instance, then you extract exactly the Poisson, the wavelet transform with respect to the Poisson, etc., etc. And this will give you the sum eventually. Okay, so you get this as like a phase retrieval problem in R2. Okay, and so basically the way that you're going to do it then is you're going to say, okay, so let's fix an element of my hyperbolic lattice. For this fixed element of the hyperbolic lattice, I get a phase retrieval problem in R2. Okay, so how do you solve the phase retrieval problem in R2? Well, you use the complement property. Now, sort of saying it like that is almost overkill because it's really quite simple here because there are really just three vectors in R2. Specifically, what happens is that for all I, from 1 to 3, there are only two options. There could either be a plus one, so either the inner product of VI with WF could be the inner product of VI with WG, or not, and in that case, the inner product with VI with WF would be minus VI, inner product with WG, again, because everything is real valued, okay? But now you have 3I and you only have two options, so either of the two options needs to come with at least 2I. So it's not possible that this is only, like you could not have that this is true for one I and this is true for one I. Then you're missing an I. And that final I either has to make this true or make this true. So either of the two, like there needs to be at least 2I for either one of these, and then if you look at these three vectors, they're full spark, so whenever you pick 2 out of the 3, you get a basis for R2. Okay, so what this tells you is that for every element of your hyperbolic lattice, you can find a sign such that WF is equal to the sign times WG. This is sort of the complement property, but in a very low-dimensional basic set. Okay, so then we use the same thing again. So we play the same trick again. Now we're going to say, okay, let us introduce H plus minus like we did before. So H plus being F plus G, H minus being F minus G. And let us also introduce S like we did before. So let us say S are all the elements BA such that sigma of BA is 1. Okay, then you think of this W that's still linear in H. So you see that W of H minus must be 0 in S. Just because, well, think about it, right? It's just linearity. And the same thing for WH plus with the complement of S. WH plus must be 0 on the complement of S. Okay. So now you unravel the definition of the W's, so you get the Poisson of H minus, the Hilbert of the Poisson of H minus, the Poisson wavelet of H plus, the Hilbert of the Poisson of H plus. Well, those are just the real part of the Cauchy wavelet transform and the imaginary part of the Cauchy wavelet transform. So all this is telling you is that on S, the Cauchy wavelet transform of H minus is 0, and on the complement, the Cauchy wavelet transform of H plus is 0. Okay, so now you see why we had P, HP, and P plus HP. So it sort of played the role of real part, imaginary part, and connecting it all together. Okay, so now the final question is, how do you go from here to saying that H minus is 0 or H plus is 0? It's sort of the final trick, because in the other situation, you had that omega has a certain property, which was positive measure, and therefore either S or the complement of S must inherit that property. Okay, this is not true here, but there is like another trick which we learned from José Luis Romero, which I'm going to show you now. So what we're going to do here is we're going to introduce these holomorphic functions on the upper half plane like we learned before. So we're not taking the Cauchy wavelet transform, but we're actually taking this a to the minus 3 half of the Cauchy wavelet transform such that we get something that is holomorphic. Okay, and then what we're doing is we're taking the multiplication of H minus with H plus, because that will be 0 on all of lambda, right? Because one is 0 on S and the other one is 0 on the complement, so the product is 0 everywhere. We call this H. Okay, so why do we do this, or why is this a good idea? Well, because while H is not necessarily in B3, like H minus and H plus would be, you can actually show quite easily that H is in B6, so it is in a Bergman space. You just have to go up with the weight a little bit. And once you have that, if you take the right lambda, so if you take a uniqueness set for the Bergman space, then you get that H must be 0 everywhere. Okay? So now H is 0 everywhere, so we have entire functions that we multiply such that they are 0 everywhere, so the two functions must be 0, one of the two functions must be 0 everywhere, and then you just unravel it in terms of H minus and H plus. So you'll find that either F is G or F is minus G. Right, so that's how this works.
Is B6 the 6 related to the density required?
Yes. Yes. Yeah, maybe I can go back. So. Yeah, exactly. So here you have is it lower or higher density? It needs to be more dense, right?
Yeah,
because you get 6 and 6. Yeah. Yeah, it is indeed. Right. So that's how it works. Yeah, and that's also actually all I have. So the final thing I want to show you is this QR code. So if you're interested in what I showed you, or if you're interested in any of the things that we used in this paper, some of which I did not talk about today, then please have a look. Please also have a look at all the papers we cite. I think all of them are nice papers. And thank you for your attention.